Okay, this is some questions from the worksheet on parametric equations. It's worksheet exercise 9E and it's called Chords of a Parabola. And in this exercise we look at finding the equation of a chord of a parabola, but using parametrics. So we'll be generally working with the parabola x squared equals 4ay, but what they're telling us here in this question is that we're looking at 2 points P and Q on the curve, x equals 2at, y equals at squared, which have parameters P and Q. Now, if we look at this, x is 2at, y equals at squared, they're the general coordinates of any point on the curve. But for point P, instead of writing 2at, at squared, point P has parameter P, so we write it as 2ap, ap squared, and point Q will be written as 2aq, aq squared. So that is the x and y value for each of the points. Now what I generally do, I put point P over here. So this is point P, 2ap, ap squared, and I like to put point Q on the other side. So point Q I'm going to put on the other side, and its coordinates are 2aq, aq squared. So in part A of the question, you're asked to show that the chord PQ, so this is the chord PQ, you have to show that the chord PQ has gradient a half bracket P plus Q. Now you'll just use the same formulas as you did when you were doing linear function. So if we want the gradient, we just use the gradient formula. So we know that the gradient formula is gradient is y2 minus y1 over x2 minus x1. We label these points x2, y2, and these 2 points here x1, y1, and you'll just find the gradient between these 2 points P and Q just as if they were numbers, okay? But instead of numbers, you've got these parameters 2ap, ap squared, 2aq, aq squared. So you just use the same formula, and we'll go y2 minus y1 is ap squared minus aq squared over x2 minus x1 is 2ap minus 2aq. Now what you need to do, you have to try and get it to look like that over there. You need to factorize anything that you can, and we've got a is a common factor on the numerator, and you've got p squared minus q squared, and on the denominator 2a is a common factor, and you've got p minus q. Now you can factorize out the numerator because that's a difference of 2 squares. That's p squared minus q squared will be p minus q, p plus q, over rewriting the denominator, 2a bracket p minus q. Now we need to cancel anything that is in common with any common factors from the numerator and the denominator. The p minus q's cancel and the a's cancel. Therefore you've got p plus q on 2. That's what the gradient is, which is what you were asked to show, that it's a half of P plus Q. Okay, that's part A of that question, to show that the chord has that gradient. Part B of the question, in this question, part B, you're asked to show that the equation of the chord PQ is this, y minus a half bracket P plus QX plus APQ. Now girls, you will do it exactly the same way as if these were 2 points with numbers. We've just found the gradient of the chord PQ. So the gradient of PQ, we just found it out in part A, was a half of P plus Q. That was the gradient of PQ. And to find the equation of the chord, you will use the point gradient formula. So you'll use y minus y1. So to do the equation of the chord, you use y minus y1 equals m bracket x minus x1. So we know what gradient we're going to use. It's a half bracket p plus q. Now for the point, you can either use point P or point Q. I like to use point P. So there's my gradient. I'm going to use that, a half bracket P plus Q. And the point that I'm going to use, because I know the gradient of this line, I just use one of the points P or Q. I'm going to use point P, which is 2ap, ap squared. So I'm going to put that into here. So this will be my gradient, and this is my point x1, y1. So y minus y1, which is y minus ap squared, equals my gradient, which is a half bracket P plus Q, times x minus x1 is 2ap. Now we just have to be really careful here, okay? We need to rearrange this and expand it. So we've got y minus AP squared. Now this is all one term. So it's a half p plus q times x, and then it's a half p plus q times 2AP. So it'll be a half p plus q is being multiplied by the x. Then it's a half p plus q is being multiplied by the 2AP. So it's a half p plus q, and that's being multiplied. So again, this is positive and that's negative. That's why I put the minus here. So it's a half p plus q is being times by the 2AP. Okay, so I've got y minus AP squared is a half bracket p plus qx. Now, a half, now we're multiplying this. Let's just do the half of 2AP first, and I get minus AP, and I've got the bracket of p plus q here. So I've done minus a half of 2AP, I get cancelling between this 2 and that 2, and I get minus AP, and then that needs to be multiplied by, still by p plus q. So I get a half bracket p plus q x minus AP squared, minus AP times p, and minus AP times q is minus APQ. So I've got y minus AP squared equals that. Now when I take this AP squared to the other side, I'll get plus AP squared, or you can just cancel them off here when you've got the same thing on both sides there, on the same thing, sorry, on opposite sides of the equal sign, it will cancel. And therefore I'll get y is a half p plus qx minus APQ. Now notice that the question is asking for it all to be brought to the left hand side and put equal to 0. So therefore y minus a half p plus qx plus APQ is equal to 0. Okay, that's part B. Now obviously you've got to be really careful here when you're multiplying this a half p plus q times the x and the half p plus q times the 2AP. Also you've got to be really careful here. I would do this half with the 2AP first, and then I would expand it with that bracket. So just be really careful there. We'll do part C now. Part C, you're asked to show that PQ intersects the directrix at that point. Again, I'm going to draw the this question out. Now we've got P and Q, and it will hit the directrix somewhere down here. So we've got P there, Q there. We know the coordinates of P, 2AP, AP squared, etc. Q is 2AQ, AQ squared. This is the parabola x squared equals 4AY. The reason we know that is that in the very beginning of the question, we were given that the parabola was x equals 2AT, y equals AT squared. Now, if you make, call those equations 1 and 2, if you make t the subject of equation 1, you get that t is x on 2a, and put that into equation 2, you get that y is a times t squared, which is a times x on 2a squared. Remember we did this last lesson. You get y is a times x squared on 4a, and you get, on 4a squared. So therefore y is x squared on 4a, and you get that x squared is 4ay. So whenever you see the parameters x is 2at, y equals at squared, we know that it is the parabola x squared is 4ay. So I know that I've got the parabola x squared is 4ay. The other thing that you will know about this parabola is that because it's the x squared equals 4ay type, the focus is 0a, and that the directrix is a units down. So the equation of the directrix is y equals minus a. And what we've been asked to do is show that this chord PQ, if you extend it, that it intersects the directrix at this point here. Now, all we know about the directrix is that we don't know its x value where the chord PQ hits the directrix. We don't know the x value, so it's some point x, but we know that the y value on the directrix is always y equals minus a. So what we're doing really is finding the intersection of the chord PQ with directrix y equals minus a. So I'm just going to write down the equation of the chord from part B. So the equation of the chord is y minus a half bracket p plus qx plus APQ is equal to 0. Now, if we want this point of intersection, where does this chord, the equation of the chord, cut the directrix? We will substitute y equals negative a into that equation of the chord, into equation of PQ, and that will give us, so when we put that in, we get negative a minus a half bracket p plus q times x plus APQ is 0. So when we substitute that y equals negative a in here, we can do that, then we can rearrange the equation to find what x is. So what I've got, I'm going to keep, I'm going to take this term here with the x to the other side, and it's that term there. The reason I'm taking it to the other side is that I've got negative a half times p plus qx. So I'm going to keep the negative a here and the plus APQ on the left. And I'm going to take this negative a half bracket p plus qx to the other side, and I get positive a half bracket p plus qx. Remember, this is one term here. Negative a is another term, and plus APQ is another term. Now, if I want to make, I want to actually, before I take this to the other side, I'm going to write it as p plus q times x. Instead of a half times that, I'm going to put it over 2. So this is minus a plus APQ is p plus q times x over 2. Now, if I want to get x on its own, what I'll do is I'll multiply the other side by 2. So I need to do 2 times negative a plus APQ. So what I'll do, I'll just put that 2 over there. So I've got p plus q times x. So I've, instead of, because I've got divide by 2 on this side, I times by 2 on the other side. And this will become minus 2a plus 2APQ equals p plus q all times x. And now what I'm going to do to get x on its own, I will just divide this side over here by the p plus q. So that way, because I've got x times this p plus q, to get rid of that and take it to the other side, it's all of that divided by p plus q. Sorry, I've run off video there. So I've got this here is equal to p plus q times x. To get the x on its own, I'll be dividing by p plus q, bring that down there. Obviously, this is not the same as what's shown in the question up here. We can see that they've pulled out a factor of 2a, so we'll pull that out. So don't pull out negative 2a because they've got a positive 2a here. So I'm pulling out positive 2a, so I'll factorise this first term here, and I get pq, and then I'll factorise this term here, and I'll get minus 1 over p plus q, and that's what x is equal to. Sorry, I'm running out of room again. So just showing that a bit more clearly. What I've got, you now look at what your answer is supposed to be, and the question was to show that this point of intersection here is 2a bracket pq minus 1 over p plus q comma a. This is almost looking like that, so what I do, I pull out a 2a as a common factor, and I'm going to factorise this one first. So I got 2a bracket the pq first and then minus 1. So I've got 2a pq minus 2a over p plus q is x. Therefore, the point on the directrix has an xy value, of course. So the point on the directrix will be this x value here that we've just worked out. So 2a bracket pq minus 1 over p plus q. And then the y value is minus a because we've substituted y equals minus a into that equation. And that's part C. And if I want to label that on the graph, so therefore this point here is 2a bracket pq minus 1 over p plus q, comma, negative a. Okay, now with these questions, I know that the algebra gets a little bit tricky, but the main thing is that you know what step you're supposed to take. So if you want the gradient of the chord, for example, you just use the gradient formula, y2 minus y1 over x2 minus x1. If you want the equation of the chord, as we did in part B, you'll use what you've always used, which is the point gradient formula. The only difference is you're not using values here, you're using 2APs and AP squareds and 2AQ, AQ squared. And to find out where this chord cuts the directrix, you're trying to find the x value here. You know that directrix is y equals minus a, you would substitute, because you know the y value at this point, you would substitute it into the equation of that line to find the x value at that point. Part D, you're asked to state the coordinates of the focus of the parabola. Now, we already looked in Part C. We said that, yes, this parabola has parameters x equals 2at, y equals at squared, and we already worked out by forming the Cartesian equation that this was the parabola x squared equals 4ay. Now, we know that with this parabola x squared equals 4ay, that the focus is a units up from the vertex, and so the focus is 0a. Okay, that's part D. In part E, you're asked to show that if PQ is a focal chord, then PQ equals -1. Now, everything that I've done in parts A, B, C, D, E, these are very, very typical questions that you could get. So here is my focus, 0A. Now, if PQ is a focal chord, it means that PQ passes through the focus. So it means PQ passes through the focus. In other words, PQ passes through the focus 0A. Now, if we know that a point lies, so in other words, the focus lies on the equation of the chord PQ. So therefore, 0A lies on the equation of the chord PQ. Now, if you look back in part B, the equation of the chord PQ is y minus a half bracket P plus QX plus APQ equals 0. So therefore, we know that the point 0A lies on this equation here. Now, whenever you know that a point lies on the line, you will substitute the point into the line. So we're going to substitute x is 0, y equals a, into the equation of PQ above. Okay, so let's do that now. Substitute, because we know that PQ passes through the point 0A, we're going to substitute 0A into the equation of PQ. So let's go. So y is a, so replacing the y with an a, minus a half bracket P plus Q. X is 0, so remember this is all one term because the three bits are multiplied together, plus APQ is equal to 0. So we've got A minus 0, in other words, just A plus 0 or just A, that becomes 0, plus APQ is equal to 0. Now what we can do here is we can either take the A to the other side, or we can factorize out the A. Now, because it's a linear function and not a quadratic function, so there are no squared terms, it would be okay to take this A to the other side if you want. So you've got A plus APQ is 0, therefore we can say APQ equals minus A. Now we can divide through by A and go that PQ is minus A on A, in other words PQ equals -1. Sorry, I'm just running off the screen there, and therefore we've shown that that result is PQ is -1. Another way of doing this is to go A plus APQ is 0, factorize out the A, but this is not necessary with a linear function. I would make sure you factorize with a quadratic function, but if you pull out the A common factor, you get A bracket 1 plus PQ. So we've got A plus is 0. Therefore, you can say that PQ plus 1 is 0. So therefore, we've got A is 0, or, solving this, 1 plus PQ is 0, or PQ plus 1 is 0. Therefore, solving this, you get PQ is -1. So it's actually okay to do it either of these methods, okay? If it's a linear function with no squared terms, you can just take the A over to the other side and divide by the A and do it this way. Both methods are acceptable, okay? All right, now for part F. Okay, now for part F, it says, hence find the point of intersection of a focal chord and the directrix. Now, in part C, we just found where, and I'll bring part C back and show you, okay? In part C, I'm just going to put it up here. We had to show that PQ, any chord PQ, intersects the directrix at this point. Now we're going to use that. It doesn't matter whether that's a focal chord or not. The chord PQ will intersect the directrix at that point there. So I'm going to write that down here. So I've got that the chord PQ, so chord PQ intersects the directrix at the point 2a bracket PQ minus 1 over P plus Q, comma A. Now that's any chord PQ, but if it's a focal chord, as we've just seen in part E, if it is a focal chord, we know that P times Q equals -1. So what we're going to do here, we need the point of intersection of the focal chord and directrix. This is the point of intersection of any chord and the directrix. Sorry, that's a minus A there as well. So therefore, if it's a focal chord, I'll just replace this PQ with a -1. So I've got 2A, replacing the PQ with a -1, I get -1 minus 1 over P plus Q, comma, -A. That's my point. And working this out, I've got 2a times -2. So 2a times -2 is -4a over P plus Q, comma, -A. So therefore, that's the point of intersection of a focal chord and the directrix. Question 4 from that same worksheet. It's worksheet 9E, chords of a parabola. In this question, we're told that P and Q are the points with parameters P and Q on the parabola x equals 2at, y equals at squared. You're asked to find the coordinates of P and Q and the focus S. So the coordinates of P would be 2AP, AP squared, and the coordinates of Q would be 2AQ, AQ squared. We know that these are the parametric equations of the parabola x squared equals 4ay. You can do that as well by making t the subject of this formula and substituting. So you get t is x on 2a and putting it into here. We've done that a few times already, and we end up with the parametric equation of x squared equals 4a. We know from this that the focal length is a, and therefore the coordinates of the focus S are 0a, because we know that this is a concave up parabola. So I'll just sketch that there and just draw again what this all represents. So we've got the points P and Q. I'm going to put point P here, which is 2AP, AP squared, and the point Q is 2AQ, AQ squared, and we know that the coordinates of the focus are 0a. Okay, now I'm not sure, remember these are points that move along depending on the value of t. Okay, so don't know exactly where the focus is, but it's definitely a units up from the vertex. Okay, now the next question says use the distance formula to find an expression for the length of PS. So we want the length of PS. So I'm just going to write down the coordinates of P. P is 2AP, AP squared, and S is the point 0a. And if you want an expression to find the length of PS, you would just use the distance formula. So the distance PS is the square root of x2 minus x1 squared plus y2 minus y1 squared. So the distance PS is the square root of, now I'm going to call this x2, y2, x1, y1. It doesn't matter which way you do it, but I'm just doing it that way. So x2 minus x1 is 2AP minus 0 squared plus y2 minus y1 is AP squared minus a all squared. And so you'll want to expand that and see if we can collect any like terms. So this would be the square root of 2AP squared would be 4a squared p squared plus, I'm going to expand this perfect square here, and it would be a squared p to the 4 minus 2 times that is minus 2 a times ap squared is a squared p squared plus this last term here squared, which is a squared. So let's see if we can collect any like terms here. Now we've got 4a squared p squared minus 2a squared p squared, so these are like terms, so you get 2a squared p squared plus a squared p to the 4 plus a squared. Now, I can see that a squared here is a common factor, so I'm going to pull that out from under there. So I've got a squared bracket 2p squared plus p4 plus 1. Now, this, I'm going to rewrite this another way around. This really is actually the square root of a squared, because if you've got the square root of something times something else, it's the square root of first thing times the square root of the second thing. Now what I'm noticing here, this to me looks like a quadratic, so I'm going to write it in the form of a quadratic. I'm going to go p4 plus 2p squared plus 1. So the square root of all this can be broken up into the square root of a squared times the square root of this. Now this to me looks like a quadratic, and it actually does look like a perfect square as well. So the square root of a squared is a. This to me looks like p squared plus 1 squared, and I'm just going to check that. If we square this, we get p to the 4 plus 2p squared plus 1, and it is. So therefore, we get a. Now, the reason you look for that is that you've got the square root sign here and you're trying to get rid of it. If this is a perfect square, then the square root and the squared will cancel. We've got a bracket p squared plus 1, because you end up with a times p squared plus 1. So therefore, that's an expression for the length of PS. Okay, we're going to go to question C. Part C, you're asked to find an expression for the length QS. Now, the only difference between Q and P is that Q is 2AQ squared, and P, if we look from before, the point P is 2AP, AP squared. So if you do the distance QS this time, you should get this same expression here, but the only difference should be that the P is replaced with a Q. Now, normally, once you've been doing this for a while, you would just say, therefore, QS is a bracket Q squared plus 1, but because you're doing this now for the first time, I actually want you to work out what the distance QS is. So we're going to go x2, y2, x1, y1. So distance is x2 minus x1 squared plus y2 minus y1 squared. So for practice, we're going to work it out, but we will get a bracket q squared plus 1, okay? So if this is x2, y2, x1, y1, x2 minus x1 is 2aq minus 0, and y2 minus y1 is aq squared minus a. And these are both squared, sorry. So now squaring this, 4aq all squared is, we get the square root of 4a squared q squared, plus squaring this, we get a squared q to the 4 minus 2 times aq squared times a is minus 2a squared q squared plus a squared. And what we get is the square root of, now 4a squared q squared minus 2a squared q squared is 2a squared q squared plus a squared q to the 4 plus a squared. Now we're going to take out a squared as a common factor, and we get a squared bracket 2q squared plus q to the 4 plus 1. Again, we see that this is, you can split up this square root sign, and we will get, just continuing here, we get that that is equal to the square root of a squared times the square root of, now I'm going to rearrange this so that the term with the highest power is first, q to the power of 4 plus 2q squared plus 1. Okay, now what we get here, the square root of a squared is a times, this here looks like a perfect square, so it's q squared plus 1 squared. And this is a times the squared and the square root cancel, and you get q squared plus 1, which is a q squared plus 1. So therefore therefore the length of QS is a q squared plus 1. Okay, now we're going to look at part D. And part D says, hence show that PS plus QS is a bracket p squared plus q squared plus 2. So let's write down what each one is. So we go PS plus QS. Now PS, if we look back in part B, was a bracket p squared plus 1. And QS, we can see from part C, is a bracket q squared plus 1. And if I expand this, I get AP squared plus A plus AQ squared plus A. And collecting like terms, I get AP squared plus AQ squared plus 2A, which is A bracket P squared plus Q squared plus 2. Okay, and that's what we've been asked to show. And now for the last question. Oopsie. Okay, now for the last part of this question. If PQ is a focal chord and hence PQ equals -1, show that PQ is equal to A bracket P plus 1 over P squared. That should be really written as A P plus 1 over P squared, like that. Okay, now I'm going to draw this question up again. Now we know that if PQ is a focal chord, so I'm going to draw it like that, it means that the chord PQ passes through the focus. So I'm just going to draw this out, that P is the point 2AP, AP squared, and Q will be the point 2AQ, AQ squared. And if it's a focal chord, it passes through the focus S, which happens to be 0A. Now, what we did in part D was we worked out that PS, so I'll just write it here, that PS plus S plus QS was this distance here. But if now we're told that PQ is a focal chord, that means, so if PQ is a focal chord, then S, the point S, 0A, lies on the chord PQ, and therefore P, S, and Q are collinear. In other words, they lie in a straight line. Okay, so therefore the length of PQ will be equal to the length of PS plus QS, which is what we worked out in part D. So it'll be A bracket P squared plus Q squared plus 2. So that's what the length of PQ is. Now, in the question you're told that if PQ is a focal chord and hence PQ is equal to -1, show that PQ equals A bracket P plus 1 over P squared. Notice here we've got that PQ so far has got A's in it, P's, Q's, and some numbers. Okay, that's a P squared, by the way. Notice what they're trying to get us to show is that PQ equals something here, but there's no Q's here. So because we know that PQ equals -1, I would make Q the subject here of this and substitute in for Q, and that way you'll get rid of the Q. So if PQ is -1, because you're told that, then Q is -1 on P, and I'm going to sub that into the into PQ, the length of PQ. Okay, so I'm going to substitute Q is -1 on P into this, so I get A bracket P squared plus, now Q squared will be -1 over P squared plus 2. So we get A bracket P squared plus 2 plus 1 on P squared. Now I'm just coming off screen there. Now again, this will be a perfect square, again, where P is your, like, A squared, and 1 on P squared is your B squared. So we're going to try this and see if this works. So if I expand this, I get P squared plus 2 times P times 1 on P. So P times 1 on P is 1, and times that by 2 and you get 2, and 1 on P squared is 1 on P squared. So therefore I get that PQ is A, P plus 1 over P squared. I think I've just done, Okay, yep, that's correct. Now, however, that looks a bit different to what they're asking us to show what it is. So what I'm going to do, it seems like we've got a common denominator here. So it's A. I'm going to write this as a common denominator as p squared plus 1 over p, all squared, okay? Girls, I've written this question here wrong. When I look back at the sheet, the squared, is actually on the outside. So, sorry about that. So this is really A bracket p plus 1 on p squared, because this is written as a sideways fraction. If the p plus 1 was all over the p, it would have brackets here, so it's just p plus 1 on p squared. So that's what we're being asked to show. If we come back down here, we've actually got that here already. So I'll just focus that. So therefore PQ is A bracket P plus 1 on P squared. So we've got A is P bracket P plus 1 on P squared. So this is your solution. You do not need to write it as that, okay? So it was finished there. Sorry about that, just the way the question was written. I didn't copy it down correctly.